Alright, I'm gonna teach you about drag. Alright, so drag is the force applied on an object as it moves through a medium. So say you have a ball moving through the air. Look, this is the air. If the ball is moving this way, the force of drag is this way. And you can just denote that F, drag. Alright, it's really simple to understand. Alright. Alright, so the key thing you need to know about drag when we're defining it mathematically is that at low speeds, at very low speeds, the force of drag is directly proportional to the velocity, but at very high speeds, it is directly proportional to the square of the velocity. Now that's very important to know. Very important. So if we want to go into more specifics, at high speed, you can define it if drag is equal to -1/2 times c, which is some constant that depends on the object, times rho. I'm going to try to draw a rho right there. Looks like a P, which is the air density. This is in air, okay? Alright, times the velocity squared, as we said before, this is at higher speeds, times the area, which is the cross-sectional area. So say you had a square, or you could say a cube. Let's say a cube. That's a cube traveling through the air. The cross-sectional area would be just the area of this face right here. That's important to know. Wait, can you cut there? And then at very low speeds, you can approximate it if of drag is equal to -b, which is some constant. It doesn't really matter. You can look it up if you want to, but that's not important for this thing. Times the velocity. So as we said before, at very low speeds, it has a linear relationship with velocity.
Alright kids, today we're going to talk about fluid dynamics. Okay, so a fluid essentially is a substance that has no fixed shape and yields easily to external pressure. Now fluid is something like a liquid or a gas. Okay, so for example, water is a fluid. Atmospheric air that we're breathing right now is a fluid. Now let's say a fluid dynamics is how do these fluids move? Okay, so we can decide, we could have this object here, circle, and it's moving through a fluid. It's going forward in the fluid. Now as it goes through this fluid, for example, it's underwater, okay? The fluid travels around it. And there's different types of ways the fluid can travel around it. So these arrows right here are flow trajectories of the flow that's traveling around it. And what you see here is known as laminar flow. Okay? So at very low speeds, fluids travel in laminar flow. Laminar flow essentially is when the fluid trajectories don't drastically change shape. They go in a relatively straight path. Now, at most practical senses, we have something called turbulent flow. And turbulent flow, essentially, is we have the same object right here, and at a very high velocity, V is a little bigger now, okay, at very high velocities, the fluids kind of form little vortexes and little eddies. So you think about like a coffee cup and the little eddies that form in your coffee cup as you stir it. That's what you can think of as turbulence, is you have all these little circles and they're kind of forming around it as the fluids continue to flow around here, but now you have all these crazy flow patterns. And the difference between laminar and turbulent flow is now all of a sudden you have all this external drag building up So it's very important, as we talked about earlier, between the difference between V and V squared. And that's when you think between laminar and turbulence. Now we're going to talk about viscosity. Now, in fluid dynamics, viscosity is the resistance of a fluid to move within itself. So, viscosity forms from internal resistance inside the fluid. And different mediums have different levels of viscosity. For example, wind has a lower level of viscosity than water. So there's more resistance to move inside of water than there is to move throughout wind or in the atmosphere. And syrup is a higher viscosity than water, so an object moving through syrup would have more resistance on it as opposed to an object moving through water, which leads to larger levels of drag on an object as it travels through syrup compared to traveling through water.
Okay, so kinetic molecular theory basically expresses fluids as the net interactions of the particles in those fluids, assuming that they all go through perfectly elastic collisions. So that means that kinetic energy is conserved. So you get equations, you know, something like this, blah, 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 equals the sum of some other particles, right? So the purpose of this with relationship to drag is essentially modeling the collisions of a gas with a object moving through it. So if I have some object moving through a fluid, right, there are going to be collisions with all those particles here, right? So the reverse action can be shown using these equations. So then at high speeds, where collisions are elastic, you get some equation like this, right? So this is because it's going so fast that the collisions are behaving very, very near perfectly elastic. So at lower speeds, the collisions are less elastic. Actually, if you go slow enough, the object will actually move at the same speed as the particles with it, which simulates sticking, which means conservation of momentum. So then you get some drag that equals just a constant times v. Just awkward.
You have to be talking straight.
I'm rolling.
Oh hey, I didn't see you there. So we're going to talk about terminal velocity now. So terminal velocity is basically the point at which drag force, that's not how you write that, equals the force due to the acceleration of gravity, right? So it is reasonable to assume that if my drag looks like this, right? So as I increase my speed, it increases in a v squared relationship, where this would be velocity, this would be drag. It makes sense that a constant acceleration, actually this would be acceleration, a constant acceleration due to gravity would intersect at some point. So essentially, the acceleration due to gravity here, the gravity force, and the drag force going in the opposite direction exactly cancel each other, and this object will be at some velocity known as terminal velocity.
And I'm free!